first of all, if Michael Beebe is here, would you see me afterwards? Secondly, I'm sorry I didn't get the slides up for this lecture till half an hour ago, but they're up now. And secondly, as promised, there are extra practice questions on ridge stuff, which you had no assignment on. So you had some of them on the practice exam, but also some more that are now on Sakai. Thirdly, because there may be a special call for office hours tomorrow since the exam's coming up, I will make it my business to be here for those at the regular time. If you need me to also be accessible virtually, send me an email. Today we're doing summary, and I encourage you to ask questions as I do the summary. But next time, well, there may be still some summary to do, but mostly next time is intended for you to ask any questions you have about the whole course. Remind you that the last assignments due Saturday so that I can see if there are any special problems that I need to talk about on Tuesday's lecture. Of course, everybody, I think, understands that the exam, the final exam, is take-home, same style as the midterm. Will be available on a week from Saturday morning and due at 11 o'clock on the day, well, on the day that the nominal final exam date would be, which I think is Tuesday the 3rd. Okay, let's go. Okay, so this slide was on at the beginning of the course. What are we interested in regard to image processing? This is a course, has been a course, on the mathematics associated with image computing. Image computing, what are the objectives? Well, the first is restoration. So if for some reason or another, well, for obvious reasons, images do not come in perfect, and you would like to improve them, that's called restoration. They are noisy. If that's your main problem, because the noise dominates the signal at high frequencies, you want to attenuate the high frequencies. Or put another way, the small levels of detail. And to do that, you do convolutions with a filter that emphasizes the low frequencies and attenuates the high frequencies. Okay, frequently a Gaussian is used, but need not be specifically a Gaussian. Okay? Images frequently are blurrier than you would like. The camera resolution was not as good as you would have liked, in which case you want to deblur, and deblurring requires you to emphasize, as frequency increases, to emphasize the somewhat higher frequencies that have been overly attenuated in the imaging process. But because there's always noise, you can't continue that forever, and you have to eventually stop overemphasizing the noise, which starts to dominate. And so the filter looks, these are all the frequency domain, look like what I call a volcano filter, because in 2D, these guys are rotated. This is rotated, and you get a sort of a volcano cone. Of course, in 3D, the same story, right? It's just in the third dimension, it's also like that. Okay. And not as restoration, but as getting out properties of the image, like edges, we frequently want to be able to apply derivatives. And derivatives, first derivative is linear in nu. First derivative of Gaussian is a Gaussian times something linear in nu. The second, and that's, say, proportional to nu. Second derivative proportional to nu squared, and so on. All those nu squared, nu cubed, are zero at nu equals 0, meaning the derivative of a constant is 0. Right? And so you end up with, in the case of first derivative, something that's going up roughly linearly, but that has to fall off due to noise. And likewise, in this guy's essentially linear. In the negative frequency dimension. And for second derivative, this should, in theory, go up like quadratic, but again, it has to turn over to deal with the noise. Okay, so those are basically the kernels we've used in this course when you want to do convolution. There are lots of other things you want to do convolution for. I use tomographic reconstruction as a very useful example. In tomographic reconstruction, you end up with images in at lots of different angles. And if you back project them all into the space, that is to say, you take one at this angle and you just constantly repeat it or, parallel to the plane that was imaged. And then you take one at a different angle and constantly repeat it and add it into the other. And you do that for all the angles. You end up with a particular blurred image that's called the back projected image. Right? And it's blurred and the kernel is known. Right? And so you do the inverse of that kernel to de-blur that back projected image. You get something that is more or less like is shaped like this, and you get tomographic reconstruction. Okay, so-called filtered back projection approach. There are lots of other algorithms for doing back projection. The main point is they have to take into account that every single one of the projection images, essentially the angulated X-rays, are going to be have some noise in them, and therefore, while the ideal filter if it were noise-free would go on forever up, it needs to be like that, and that, of course, limits the overall resolution that CT can produce. The last restoration objective that one is concerned with images is that they sometimes distorted. Distortion means the positions at which the intensities appear are in the wrong place, right? And to overcome distortion, you need to apply a geometric operator to undistort. And we discussed how to apply geometric operators. If you know what the distortion is, you can calculate what the undistortion should be, the operator, and apply it to the image, and you get a less distorted image. Any questions about that? Okay, then image analysis is about lots of things, but a whole lot of it is about finding objects in the images. And finding objects is typically done by applying edge strength or bar strength. I call it edgeness or barness here. Operators to, and then essentially running a ridge operator, which we also talked about just recently, to find the actual locus of the edges of an object, and thereby to be able to pick out the object. There are lots of other ways of doing so. This whole process of segmentation is covered in far more detail in COM 775. It's also cross-listed in BME. Should you be around in the fall and want to endure another semester with me, you are welcome to register for this course. It's a graduate level course, but even if you're an undergraduate senior, if you come to me, I can give you permission to register for that. Another objective that one frequently wants to do is to reform the image. We may find that due to computational needs, or just because after processing the images are at lower, poorer resolution, and therefore you can, without losing much information at all, change the sampling rate. And so we've talked about how to change sampling, which involves doing rect and then resampling at the new level. And of course, we also talked about how to understand the amount of pollution at any given level of sampling. And we came up with a formula that turns the amount of pollution you're willing to endure and the RMS width of the blurring that's in the image into a sampling rate, into a delta X. We also typically want to do sampling because to do localization, which is really important to focus on particular areas of the image, you need to do multi-scale analysis. And when you do multi-scale analysis, you're successively blurring, successively applying a low pass Gaussian filter. And as a result, you can satisfactorily subsample. And so you get this sort of pyramid effect that the top of the pyramid, which is at the least resolution, the widest level of detail, can be much more coarsely sampled than at the lower levels of resolution. And therefore, when you're doing this multi-scale idea, you end up doing changes in sampling. Questions so far? Another kind of reformation is taking your image and shifting it or rotating it or registering it deformably to bring it together with some reference situation in which we can better do, for example, segmentation, finding the objects, okay? And so we have sometimes the object that we're interested in is here in the image, and sometimes it's here in the image. And if we could bring them together so that they're both here together, then we can do statistics on the shape, or we can use a template that says the object looks like this, and we can use that to help segment the object. And so the idea is to be able to bring everything into the same orientation or the same position by translation, or the same scale, and spatial scale. And so we studied in this course how to accomplish those transformations. And we saw homogeneous coordinates as a means of doing it via essentially matrix multiplication means, and for the particular pair of scaling and rotation, we saw this powerful way of doing it via quaternions. The next thing is visualizing the images. Visualizing is basically preparing an image to present to a human. That's essentially what it's for. There's all sorts of interesting things to do in regard to the contrast of 2D images, or in standardization across display devices, right? You'd like in a medical situation, the particular display that one physician sees on his display device to be similar to the one he sees on the other display device, and that depends on making measurements on the specific display devices, and then compensating for the particular way in which numbers, display levels that go from, well, the cheap displays go from 0 to 255 in their intensities, but the better ones have 12 bits rather than 8 bits of intensity. And the question is, you have those numbers from 0 to, if it's 12 bits, what is that, 4095? And how do those go into intensities that appear on the screen, right? And that mapping function turns out to be useful to deal with. Likewise, you have the objective of contrast enhancement. That is to say, you would like some perhaps too low contrast changes to appear as higher contrast changes. We haven't discussed that in this course, but there's a great deal, well, there's a good deal understood about that. And I just mentioned, well, that and the fact that I spent, 6 or 10 years of my career worrying about contrast enhancement and standardization. But the visualization thing that's more relevant, more related to the material in this course is the 3D rendering problem. Okay, so in 3D rendering, essentially what you're doing is you're finding surfaces and you're simulating the reflection of light off those 3D surfaces to get a rendered image. That is to say, a display that you can then rotate and view. It's being used a great deal these days in medicine, so very routinely. Probably the most dramatic one is doing it from ultrasound in obstetric situations where folks can see their fetus before the baby's born. But it's used for quite a wide variety of things. And to do that, you need to be able to find your edges and to use your edges and their orientation to do the simulated lighting. And so the stuff we've done in this course is very relevant to that as well. Turns out that this, again, here at UNC, we made very, very early major contributions to the techniques that were done there. In fact, there's a technique called volume rendering that was more or less simultaneously worked on at 3 different places in the world, in the United States actually, and one of them was here. And what can I say? The one that actually had the first accomplishment was an industry place, and they're not inclined to publish these things early, and so they didn't, and we did. And so the first publication in that volume rendering was, in fact, by Marc Lavoie et al., of which I'm part of the all, which came out of UNC. Okay, anyway, the next thing is these applications where you have a 3D image. Most of the images we take with ordinary cameras are not 3D, they're 2D images. In microscopy, you have a technique that essentially gives you a pile of slices, essentially with the stuff that's out of slice a bit blurred and the stuff that's in slice sharp. And so you end up with a 3D image, which is that pile of slices. And then you want to visualize it not necessarily either in full 3D or in directions that were other than the direction of the pile of slices. In MRI, in medicine, what it normally produces is a pile of slices, essentially reconstruct slice by slice. And CT often is made slice by slice as well. The reason being that there is an effect of the scattering of X-rays that you can limit if you do it slice by slice rather than try to do it instead of you use a fan beam rather than a cone beam of X-rays in order to do it slice by slice and thereby throw away the stuff that's outside of the plane of the fan. And the result is that it ends up giving you slice by slice ways of producing 3D images. And once you have slice by slice, you may want to reslice it, or which we studied, or you may want to take a particular 3D image and turn it back into slice images that people can see. We studied how to do projections and how to slice through 3D images to get visualizations of those particular slices. Questions? Okay. One more slide on the objectives. Because images are so large, you may want to compress them for either storage or transmission. And we talked about how to do this compression based on eigen images of from training images that produce examples. This produces what's called a lossy compression. It's not a compression that is completely captures all the information in the image, but it loses very little because you cut off which eigen images you have only after they capture very little signal. Mostly, in fact, noise. Again, the noise appears through many levels of detail, whereas the signal tends to drop off at the smaller levels of detail, higher frequencies if you want to think in terms of frequency, smaller wavelengths. And as a result, you can throw away the parts of the image that are basically about noise anyway. And although you lose a little bit of signal, it's heavily corrupted signal. It's useless signal, if you will, because it's so dominated by noise. And therefore, you get good compression, better compression than you get by untrained means. These days, training is often done by deep learners. Deep learners are the first order about optimization of certain properties by giving a heck of a lot of examples. You give it something you want to optimize and it figures out what the convolutions are ultimately. There are some nonlinear components in there too, but mostly it's about figuring out what the convolution kernels are going to be that optimize your objective, that minimize your so-called losses. We've talked about registration already, but briefly, a moment ago. But the main point here is that if you have two images or more that you want to bring together into one ideally undeformed, well, you can have one that you want to register every other one with. You need to be able to find the optimal deformation. We talked about ways to represent deformations. One of them was using an image of displacements, but typically not done as a fully an initial value for every pixel of voxel, but rather approximated by a coarse set of displacements, which can then be interpolated into a finer one by, for example, Catmull-Clark or spline methods. Catmull-Clark in the limit is a spline-based method. And in COM 775, you will hear a whole lot more about registration. The interesting math of registration is deep and exciting to learn about. But essentially what you learn about is that you have a very high dimensional space of deformations. Okay, so a point in here is a deformation, a whole deformation. And you're trying to find the best place, and you're starting from the identity deformation, and you're trying to find a path of deformations, of small deformations, to get you up to the ideal deformation. And it's a very interesting set of techniques that go under the name LDDMM, large deformation diffeomorphic metric mapping, that basically involves optimization with constraints, and optimization with constraints is done with Lagrange multipliers, but here the Lagrange multipliers turn out to be variable with position. And so you end up with a whole image of intensities and a whole image of Lagrange multipliers. Okay, and you end up with some set of Lagrange multipliers going up here and fixing the Lagrange multipliers coming back, and you iterate that process and you end up with very nice registration methods. Not at the level we've talked about here, but the background we've done to understand how deformations are done and how you do this. The target image is at some pixelization of voxelization, and you're applying the inverse of the deformation from the source image to the target image in order to get your result. We saw that very recently. And I've also talked about the display of 2D images and 3D images. Questions on anything? Okay, so I've gone through the objectives that we were concerned with. This course wasn't really about the objectives. It was about the mathematics that you and the algorithms that you needed to achieve those objectives, as motivated by those objectives. And so now the rest of these slides are a reorganization of the things that we covered in this course. We saw that for computational efficiency, having orthogonality was a very desirable property. And it's essentially because if you have orthogonal bases and you want to expand an entity, an image, for example, in terms of the orthogonal bases, the way the coefficients are computed by dot product. That is to say, if you have an image and you want to talk about it as some ai psi I, and the psi i's are images, then the ai's are simply I dot psi I, if these are orthonormal bases. Right? Very, very important thing. It's way, way cheaper than when you don't have orthonormal bases. If you don't, you end up having to solve large sets of linear equations for the AIs, even if you're in this idea where you're trying to expand, but now you have to solve for the AIs with a big matrix times A equals some result B. And you solve those linear equations, and since there are so many A's, right, if you're trying to, typically, there are n squared or n cubed of these, and so n squared or n cubed of these, and so therefore n squared or n cubed of these. And so this thing ends up being an n squared by n squared or an n cubed by n cubed size matrix. And that's a big matrix to try to solve for, and you'd rather not do it. And therefore, the orthogonal bases are really interesting. And so the first set of orthogonal basis images that we talked about were the sinusoidal images. And they are generally useful, but they're particularly useful because they are the eigenimages of shift invariant linear operators, right? And so the point being that once you have that, when you want to apply one of those operators, the T simply multiplies psi I by the eigenvalue. Okay? And that decoupling that makes you not have any other terms when you apply T to psi I, only one in psi I, is very useful, and we may take advantage of that by first solving for the AIs and then multiplying the AIs by the lambda i's. And we do all that. Well, we could do it by dot product, but for the sinusoids, you have an extra advantage that there exists a divide and conquer algorithm that goes even faster for kernels of any reasonable size. The kind of size we're talking about for 3D, beyond 3 by 3 by 3 kernels or so, it turns out to be cheaper to do it via going over in the frequency domain. For little tiny ones like 3 by 3 by 3 kernels, it's cheaper to do it in space. For 2D, maybe 5 by 5. But once you start getting bigger than 5 by 5 sort of kernels, then it's cheaper to go via the frequency domain. Okay, and when you go via the frequency domain, you can take advantage of this cheap multiplication because it's done I by I. That is to say, eigenvector by eigenvector. That is to say, sinusoid by sinusoid. And although the whole business is a bit complex because of the fact that the eigenvectors actually are pairs, a cosine term and a sine term, or a magnitude term and a phase term, or a real term and an imaginary term, depending on how you think about it. Nevertheless, it's basically this story. Any questions about that? I'm assuming you're going to break in if you have questions. We also saw that if you have a training matrix of images and you want to get this compression, what you're looking for is the eigenvectors of this A transpose A in order, decreasing order of its non-negative eigenvalues. And you take the first so many of those, and you use those as the psi i's. And we saw the particular technique of computationally improving this in the situation where the number of training images is less than the number of voxels. And by actually doing your eigenanalysis on a transpose and then doing a transformation, so you get lambda i's and ui's, eigenvalues and eigenvectors from this, and it turns out the eigenvalues are the same, and the vi's are just A transpose times the ui's. So there's a linear transformation to turn the eigenvectors of A transpose into the eigenvectors of A transpose A. And those are what you need to do the dot products for other images that you want to compress. Got it? Orthogonality was also important to us for multiscale analysis. And those are provided by the orthogonal wavelets. Again, that means that the features you come out with are done by dot products, right? The coefficients of the orthogonal wavelets at various frequencies. And the only problem with them is that they are neither translation nor orientation invariant. And since for finding objects, orientation and rotation invariance is of importance, you need to either pre-process by a registration process that I just talked about to normalize out the rotations and translations, or you are in trouble with using the orthogonal wavelets. I remind you, the major purpose of the orthogonality is computational, because it supports this faster computation by dot product. So when you don't use orthogonality, you're going to pay for it in computing time. and sometimes a whole lot of computing time. Then we talked about least squares approximation, where you're essentially getting rid of noise to some degree by producing an interpolation that doesn't require the resulting image to actually pass through the pixel values. And that ends up also with an ability to solve things by dot product if you are representing the image as a linear combination of orthogonal functions. The most common use of that is for orthogonal polynomial functions, but it works for any set of functions that you might have. You can orthogonalize them. Briefly mentioned the Gram-Schmidt process of turning a set of non-orthogonal ones over a set of points into orthogonal ones. And the difficulty there is that often in the applications, the data points that you want to fit with least squares are not the same from application to application, but the orthogonality depends on what the set of points in the image space are, where the data points are. We also talked about various non-orthogonal bases. Taylor series, useful only very, very locally, too locally. Not with the kind of locality that we talked about with Gaussians, where we're talking about locality in a notable section of the image, and say a section of an object or a major part of an object, as opposed to these little, way too local approximation with Taylor series. But we noted that it has basis images, they're polynomials. Piecewise polynomials, though, are much more powerful. So we talked about B-splines, which are piecewise cubics, but there exist splines with piecewise quadratics or piecewise quartics or what have you. And these piecewise approximations are smooth. That is to say, they're done patch by patch for locality. And the computation for any given patch uses an aperture that is centered at that patch. That is to say, it uses data, control values, in this aperture to produce the polynomial in the patch. And then the patches fit together smoothly, and now you have locality. And on top of that, you can play the game of multiscale, of initially using large scale, large patches, seeing what that gives you as an approximation, subtracting the approximation from the original image or whatever that you're trying to approximate, getting, therefore, what yet needs to be approximated, and then using smaller patches to give you an additional piece of the approximation which comes from the smaller scale, and you play that game iteratively. The B-splines use the polynomial basis images. It turns out there exist splines that use these radial basis functions, basis images, that we saw first when we talked about thin plate splines, whereas the approximation that you do for B-splines requires everything to be gridded up, right? All the control values are in a grid. Let me erase some. in the thin plate spline situation, the places where you have data, which are typically landmarks, can be non-grids, and you end up with a approximation of the form a x prime, which is of the form ax plus b plus some I wi u of x minus xi. Distance. Scalar functions. And these scalar functions of the distance you're at, the position you're at, relative to the data positions are the radial basis functions. We saw that for this particular problem, they are known for both 2D and 3D. And there's nothing that says you couldn't apply this thin plate splines idea for gridded. For the situation where the control positions are gridded, we are in an orthogonal grid. We saw that a very ideal basis from a theoretical point of view were Gaussian derivatives. And indeed, we saw that whenever we want to take a derivative, we should think that there's always an aperture, and you need to worry about what the aperture is. And the aperture function ideally is a Gaussian, which means, by virtue of the fact that that convolution, well, that cascading of shift invariant linear operators is associative and commutative, means that essentially what you want to do is apply the Gaussian and then apply the derivative operator all in the frequency domain. But ultimately what that means is you're writing down an image in terms of a linear combination of Gaussian derivative applications to the image, which is to say you're using the Gaussian derivatives as the basis. And the difficulty is that they're not an orthogonal basis, so computationally they cause some difficulty, but nevertheless, because they can be applied over in the frequency domain, and that's pretty efficient, it's not ideal, but it's still quite good. And so doing your work with the Gaussian derivatives to give you residues is a very powerful method, and the residues are frequently can be understood as Laplacian of Gaussian. They're called logs, right? Laplacians of Gaussians as the operators, but because the Laplacian is approximately the difference between Gaussians, the Laplacian operator is approximately the same in the frequency domain, let's say, as the difference between Gaussians at two different sigmas, at two different RMS widths. We typically use this difference of Gaussians, which makes it clear that what we're talking about is the residues between one scale and the other scale that are producing the difference. We also saw that some people favor the Gabor wavelets. They have the nice property that the level of detail, the wavelength, is fixed. for a Gabor wavelet, right? You still have the Gaussian envelope, but unlike the derivatives of Gaussians, where the maxima and minima, the wavelength, the waves are not from one. The wavelength is not the same for the first interval than for the second interval between the second max and the third, and so on. Whereas for the Gabor wavelets, it is, right? Because you got a sinusoid under a Gaussian. And for a sinusoid, the maxima are, for every interval, is this essentially the same, except for very minor differences as a result of the multiplication by the Gaussian. Anyway, that fact and the fact that texture tends to be at least locally having some regularity in level of detail and width of the textons, so-called, means that the Gabor wavelets are used very frequently for situations when you want to do texture analysis. And texture analysis is underrated. In ultrasound images, for example, there are basically two sources of information about the objects that they're trying to look at. One of them is the fact that you get echoes off of tissues with different sound transmission properties. And but because ultrasound is basically sound, it's looking at echoes. And if you're insulating from this direction and the boundary is like that, you get a bounce like that. And since your receiver is at the same place where your transmitter is, you never hear that. And so you only see this for surfaces that are more or less orthogonal to the intonation level. And so the point is the information on boundaries that you get from ultrasound tends to be a bit of strong boundary, and then it goes away because it's not facing the intonator and so on. And you need to depend on the other property of ultrasound that deals with what happens at the microscopic level, if you will, at the cell size level. And the point is, different tissue types not only differ in their ability to transmit and thus echo sound, but they also differ in the interaction at small frequencies, at small size entities, at the cell size. And it turns out that those show themselves as textures. And therefore, ultrasound image analysis is frequently done by looking at texture differences between regions rather than intensity differences between regions. And anyway, to make this story finish, when you want to do texture analysis, whether in medical images or in real images, the Gabor wavelets have been frequently used. We spent a lot of time in this course thinking about invariance. And that's because in images, you can't depend that an object will be viewed at a particular orientation that's the same for every case, or with the target in a particular position, which may vary case by case, or possibly you're closer or you're farther away, and you get scale differences. And therefore, it was important when you do the analysis to come up with operators that weren't going to be sensitive to the shift or the rotation of the scale. Or to put another way, when you re-rotated them by a registration, you got essentially the same result as if you would have applied it in the first place and rotated it later. or done whatever the geometric operation here is. And so we therefore were very pleased with the fact that the Gaussians specially have these invariance properties, and the sinusoids specially have these properties of invariance. Okay, I've already said we understand the application of shift invariant operators by understanding them in terms of amplitude and phase, and realizing that the amplitude transformations aren't enough, that phase is really an important property of images when you're trying to get information about objects. We understood that operating in the frequency domain was a means of doing convolution, albeit a convolution that necessarily had this periodic property, which ended up meaning that at the edges you were typically polluting the right side with the left side and the top with the bottom. Okay, but we did it in the frequency domain. Why? Because it was fast. Because we could use the divide and conquer algorithm, and that was computationally important. We understood convolution in the space domain as having a kernel, and the kernel being what a impulse, a delta function, turned into, and therefore what any given pixel or voxel turned into, but that when we looked at it in terms of an output as affected by a variety of inputs, it was the reflection of the kernel. That was the weighting function. And in the frequency domain, we're looking at multiplication by the transfer function, or equivalently the filter, right, which I've drew earlier. I've already talked about the derivatives. Derivatives that we care about are typically in special directions. The gradient, which is the strongest indicator, the gradient vector, and I want to make sure that you all understand that some people misuse the word gradient when they mean gradient magnitude. Please don't do that yourself. Gradient means a vector. Gradient magnitude means a scalar value, right? And the direction of the gradient is the most important direction to take your derivatives in. In fact, the derivative value in the gradient direction is the gradient magnitude. And that's the strongest, the biggest derivative you can get over all possible directions of derivatives. But because you get the gradient direction, if you rotate the image, then the gradient direction correspondingly rotates. You're okay with regard to slightly rotated images because you'll still be able to apply the gradient in the right direction, the derivatives in the right direction. I already talked about derivatives via the Fourier basis functions and doing it with a Gaussian. We studied spatial sampling and understood that that could be understood in the frequency domain, or understood as convolutions. And we ended up seeing this idea that if you knew the blur level of the image, the RMS width of the point spread function of the image, and you knew that by taking a picture of a point, and that gave you the point spread function. You get its RMS width and call it sigma. And since it would be approximately Gaussian, that for any given level of pollution, you can figure out, that you're willing to accept, you can get the intersample distance, how far apart the pixels of voxels should be. Going through this fast, questions? We also talked about interpolation. And interpolation, or its generalization approximation, are shift invariant linear operators. You want them to be. Therefore, they're associated with kernels. Therefore, they're associated with transfer functions. And the transfer functions show us that, except for the ideal interpolator, ideal only in the sense that it's perfect for noise-free images with infinite all the full range of possible resolutions, which is the sinc function, but which is not particularly useful because of this ringing effect that it produces off of edges. We will not use the sinc function, we'll use something else. And each one of the else's, each one of the alternatives, should be understood in terms of the amount of blurring that it produces. End of this slide. We saw that separability was a desirable property because it saved some computation. In some cases, it was the way the operators were defined. So orthogonal wavelets don't exist in 2D and 3D. They only exist in 1D, and then you apply them separably to get 2D or 3D effects. That is to inseparable operation. You are applying things in one dimension only. I'll call it row-wise. You get a set of results, and you use those as the inputs to an application column-wise. And if you have a third dimension, then you take those results and apply depth-wise. That means the applications are 1D applications. So if you have an n by n by n 3D image, you have n squared 1D n tuples. And you have n squared of 1D applications. And then when you go in the other direction, you have a different n squared 1D applications on the results of the first. And then in the third dimension, you get another. And the total computation time is 3n squared times the time for applying in 1D, which, if you're doing it sinusoidally, will be n log n. Times a constant. And if you do it and doing it in space, it will be n times little m, where little m is the size of your kernel times a constant. In any case, separable is advantageous computationally, and you get it for free when your operator is itself separable, as as is the case for sinusoids, or you get it because you're building that in to something that you're applying, you've defined separately. The splines are defined separately. And orthogonal wavelets, likewise, applied separately. We spent a good deal of attention on the notions of locality and scale. The idea being that you wanted to be able to analyze it at any given center point in the image with regard to a region of the image determined by what we call the aperture function. And the ideal aperture function was the Gaussian, and thus the kind of width we associated was the RMS width, the sigma of the Gaussian. And we saw also that there was once you had a particular sigma, there was an issue of level of detail, which was essentially wavelength for things that are sinusoidal, order of the derivative if you're doing things in terms of Gaussian derivatives, and similar, this binary subdivision level if you're talking about orthogonal wavelets. We saw the Gaussian was the ideal aperture, and it's worth you looking up what we required of it, but I'll repeat it. There were the three invariances that I just talked about: scale, uniform scaling, that is to rotation and translation. And admittedly, these are properties that are about essentially infinite images and don't take into account that our images are cut off, and when you do translations, things actually translate out of the image. But also, we wanted this property that so separate rescalings, since we want to work in scale space, we want to be able to rescale and scale again the result and so on, produces the same as a single scaling, not scaling, a single aperture application. That applying an aperture to one aperture and the result with another delta aperture, if you will, produced the same effect as producing a combined aperture. And that plus this not wanting to have arbitrary properties appear out of nowhere, that you could only lose structure and not get extra structure, produced the desire to have the Gaussian aperture. And that's why we spent so much time on it. We saw that splines applied separately are not rotation invariant, but they were nevertheless quite a useful operator that could be done rather more easily by the successive subdivision route rather than direct application of the spline idea. And they're very nice properties of allowing a multi-scale application. Large scale, control points, next lower scale, and so on, was a powerful property that was frequently used and used very much in the free-form representation of displacement for registration that you saw exemplified in your assignment 7. So you needed to learn, I mean, we were using it just there for a rotation, and you really wouldn't, in the real world, have the the displacements correspond to only a rotation, because you could do rotation much faster, for example, via quaternions. But that idea, when the displacements were not consistent with a pure rotation, is the most common way of representing deformable registrations. We saw that, at least for the purpose of finding objects and object properties, Gaussian derivatives, the Gabor images produce similar results. But the advantage of the Gaussian derivatives dominate, but not for texture. The orthogonal wavelets are orthogonal, but only with respect to these binary translations, right? So 1/2 of the image to the other half, 1/4 of the image to the next quarter, and so on. But when you had translations other than those, they were not even orthogonal. We saw that this general idea of applying an aperture and looking at the difference between the application of that aperture and a smaller aperture produced what we call residues, those differences. And that was a particularly powerful way to get a scale space, a space of representations at multiple levels of scale that combine to build up the description of the image at a succession of scales. And that was sometimes worked as large scale to small, or sometimes small scale to large. Okay, properties that operators can have. Isotropism, meaning that the effect, essentially the convolution kernel is rotationally symmetric. Okay, so it's circularly symmetric in 2D, it's spherically symmetric in 3D, and therefore means that you can deal with rotation very nicely. And since Gaussians and sinusoids have that property, that they're great from that point of view, but that the splines, the orthogonal wavelets, and these interpolations that go in X then Y or Y then X, for example, like bilinear, trilinear, are not isotropic. Separable application of the first kind is perfect. Separable application, which you're forced to in the second, have properties of bias towards the specific vertical and horizontal directions. We realized that we needed to understand what invariance was. We used that idea very much, and that definition was important. And we saw that the wavelets and the splines have invariance weaknesses, the orthogonal wavelets and splines. And then the other part, yeah?
For the non-isotropic operators, it seems like it's possible you could assign weight to one direction or another to sort of make it isotropic in whatever property you're looking for. Is that possible or not? Not really. Like if you know the geometry of your operator, you compensate for that to sort of make it isotropic.
You can analyze locally what the important directions are, and then apply the non-isotropic operator in those orientations. And then it requires that special analysis step of figuring out what are the ideal directions. So yes, in essence, you can do that. And then, from a computational point of view, the big deal is whether there's a divide and conquer algorithm, because that means you don't have to use even dot products. And that's what you get from the sinusoids. That's the big deal. That's a major reason why I use the sinusoids, other than the fact that they're also isotropic, have this nice isotropic property. Okay, I'm just going to stop now. The next group of these slides, which I can pass through quickly and see what kind of questions are exactly the same slides that I used for the midterm. And so, well, you've seen them. And so I'm going to start next class by taking questions. And if the questions run out, we'll pass through these other slides. Otherwise, you can go restudy them for the final. Questions before we end? Okay, see you on Tuesday.